Okay, so today we're going to look at non-ohmic resistors. So in today's lesson, there's 3 learning objectives. We're going to describe the effect of the resistance of light-dependent resistors on brightness, so how brightness affects light-dependent resistance, and how resistance in thermistors is affected by changes in temperature. We're also going to know that LEDs are used to indicate the presence of a current in a circuit, and we're going to become familiar with the equation energy transferred in a circuit equals the charge in that circuit times the voltage in that circuit. So the first thing is, let's look at an example of a non-ohmic resistor, a filament lamp. Okay, so if you repeat the experiment of measuring the voltage across a filament lamp and also measuring the current in the circuit, and you plot the current of the circuit against the voltage across the filament lamp, you will see that it is not a straight line. And the reason why is that as the voltage increases, the temperature of the filament lamp increases and the resistance therefore goes down, because at higher temperatures resistance is lower. And because it's not a straight line, it's a non-linear relationship, current is not proportional to voltage, we say that the lamp is a non-ohmic resistor. Okay, it doesn't follow Ohm's law, V equals IR. So another example is a diode. So a diode, current only flows in one direction, which is given by the direction of the arrow, because in the opposite direction the resistance is just too high that current cannot flow in the opposite direction. And these pictures here are examples of light-emitting diodes, or LEDs, and they release light when the current flows through them. Okay, and that will show you that if your LED is going, it means that current is going through the circuit. And there's 2 special types of resistors that you have to know. The first one is the thermistor. Okay, so the resistance in a thermistor goes down or decreases as temperature increases. And you can see this from a plot of current versus voltage. The higher temperature line, the red line, the hot line, is a greater slope than that of the colder temperature. Because remembering the gradient of the current voltage graph is 1 over the resistance. So it means that the higher the gradient, the lower the resistance. It's an inverse relationship. And the same is the case for the LDR, or light-dependent resistance. If the resistance of the light-dependent resistor goes down or decreases as light intensity increases. And again, you can see this from the graph of current versus voltage, that the bright light has a higher gradient, or a greater gradient, than the case with a dim light. Finally, let's look at the energy transferred equation. So the energy transferred in a circuit equals the charge in that circuit times the voltage in that circuit, where voltage is in volts, energy is in joules, and charge is in coulombs. And of course, you have to be able to rearrange the equation. So also the charge in a circuit equals the energy transferred in the circuit divided by the voltage in the circuit, and the voltage in the circuit equals the energy transferred in the circuit divided by the charge in that circuit. Okay, and that is today's lesson.